Okay, good morning, everyone. Uh, do you guys have any question regarding this Lagrangian and this Hamiltonian so far? Today will be the last class for Unit 1, most likely.
Sir, could you please repeat what you said?
I just ask you that whether you have any questions or not regarding this Lagrangian or Hamiltonian. Did you guys try to solve any of this problem in the tutorial on the Lagrangian? Setting up the Lagrangian and trying to derive the equation of motion. Any of you tried so far? I gave you I think three problems on the tutorial set. Has any of you tried any of those problems? See, I'm repeating again and again. These are the type of question that you can expect in the quiz or in the mid sem or in the end sem. And this is the time that you will get chance to solve this problem. And once this time passes, there will be no more tutorial on these problems and so on. So you will get new set of problems. So if you don't practice right now, you will be in trouble because we will not stop on this Lagrangian. We'll continuously move on to the next and next chapters. Okay, so if you guys don't practice right now, I don't think you will get enough time to practice. For example, you will have mid sem within 2 or 3 weeks. So if you don't practice right now, so you will not get chance to practice these things later. And also you guys will be moving in the next week. So please try to solve those problems and try to see how set up this, try to learn about this Lagrangian and this Lagrange's equation of motion. Okay.
Sir, what is the syllabus for mid semester?
Unit 1 and Unit 2. Unit 1 we have almost covered. As I told you that today will be the last lecture of Unit 1.
Okay, sir.
And Unit 2 we will start from tomorrow, Unit 2. That will be on thermal physics. So you will not get like holidays before mid-sem that you will get a 1 week leave before in-sem, not like that. So immediately after exam, maybe you will get 1 or 2 days. Maybe, I'm not sure that also. Maybe within 1 day you have to sit for mid-sem. Okay. So you guys be prepared. You will not get the chance that there will be 15 days holiday for your mid-sem or some, not like that. So immediately when the class stops, within 1 or 2 days, you have to sit for mid-sem and you have to you have to solve all this problem on the question papers.
Would class continue in mid-sem?
Sorry?
Would class would be taken during mid-sems?
No, will not have any class, but let's say your mid-sem start from 25th of September, we'll have class continuously up to 23rd September. So maybe we'll get one day break before mid-sem. And that time you will not get any support. That you have problem that time you will try to solve, you will not get any support that time. So whatever problem you have, you try to practice them right now and let me know if you guys are having any trouble in solving those problems. If you guys don't tell me what are the problems, then I cannot help you. You have to tell me what are the problems you are facing in solving this problem. Then only I can help you. So start practicing these problems on this uh, generalized coordinates, Lagrangian. I know vectors. Some of you are familiar with this vector calculus and can solve those problems. But still, you should practice those surface integration because those I think new for many of you. So start practicing problem on those whatever new you have learned. You start solving problems on those. You see how to set up the Lagrangian in the problem set I have given in the tutorial, okay? And we will discuss this on Thursday. But if you guys don't practice, then there will be no point of discussing on the tutorial. So please practice. Okay, so if you guys don't have question, let me share my screen and then today we'll set up the Hamilton's equation of motion and then I'll show you some examples how to solve those problems. Okay, so in the last lecture, we have derived this. We have basically we have seen the expression for the Hamiltonian that by considering few assumptions, if you can get this form of the Hamiltonian. You by considering few assumption, you can show that Hamiltonian is basically the total energy of the system. That Hamiltonian you can write as T plus V. But that is only for a special case. But in general, that you can write the Hamiltonian. In general, you can write the Hamiltonian of any system. This is like H equal to Qj dot Pj minus L. But Pj is the generalized momentum. Qj is the differentiation of the generalized coordinate J, and L is the Lagrangian. The important thing here is that this is summation over J. So if you have two or more generalized coordinates, then you have to do this summation. Okay. If you have only one generalized coordinate, then it's fine. But if you have, for example, those problem of central force problem, there you have two generalized coordinate r and theta. So there in that case, you have to consider this summation. You have to do this first term. For the first time, you have to consider the summation over both r and theta in case of central force problem. Okay. Now from this Hamiltonian, what we want to do, we want to set up the Hamilton's canonical equation of motion. That once you know the Hamiltonian of the system, once you set up the Hamiltonian, how to derive the equation of motion. Okay. So now H is given by this formula. So what? Okay, and L Lagrangian, we know Lagrangian is generally a function of the generalized coordinates, is derivative, and the time. This is the general formula, general functional form of the Lagrangian. It depends on Qj dot, and T. Okay. So now what you can write about dl, that if you take differentiation of the Lagrangian, what you will get? You will get the partial derivative with respect to Qj, and you will get dQj plus summation over j del L del Qj dot dQj dot plus del L del T dt. This will be the form of dl. If Lagrange, when as you know the Lagrangian depends on this, the Lagrangian has this functional form. Okay. Okay, now let's say this is equation 1. And now I told you that Hamiltonian is given by this functional form. So now see what is dH looks like. So H is basically summation over j Qj dot Pj minus L. So what you can write about dH? dH will be basically, this is summation over j Qj dot dpj, okay, plus summation over j pj dqj dot, okay, and minus dl, because you have this Lagrangian here. Now you replace this dl express, you put this dl from equation 1. You take this expression of dl from equation 1 and put this form here, okay. Then what this will look like? This will be summation over j qj dot dpj plus summation over j pj dqj dot minus dl. What is dl? dl is this form, that summation over j del l del qj dqj plus summation over j del l del qj dot dqj dot, this is not plus, this should be minus, right? And this is also minus del l del t dt, okay. Now what is del l del qj? Can you guys tell me what is del l del qj? We have learned about this in the last class. What is del L del Qj and what is del L del Qj dot? Can you guys remember what is the formula for this generalized momentum? Anyone?
Del L by del QG dot.
Del L del Qj. This is what?
Generalized momentum del L by del QG dot.
Del L del Qj is not the generalized momentum. We have done this in the last class. The generalized momentum Pj is given by del L del Qj dot. This is the generalized momentum. And from the Lagrange's equation of motion, I showed you that if you then Pj dot will be del L del Qj. This we have done in the previous class, okay. So what we can write, instead of del L del Qj, we can write Pj dot. Or and instead of del L del Qj dot, we can put Pj there. So this will be simply, this will be minus del L del Qj is Pj dot dQj minus del L del Qj dot, that is Pj dQj dot minus this del L del T will be there as usual, okay. So this will be del L del T dt. Now you can see this term is there as a plus as well as minus, Pj dQj dot and Pj dQj dot. So this will be cancelled, okay. So effectively you will get j qj dot dpj minus j pj dqj minus del L del T dt, okay. This is what you get for dh, okay. Now h is also a function of, I told you that h is a function of qj, pj and t. If you look at the functional form of h, it depends on the generalized coordinate qj dot and l, or this sometimes it depends, l has qj and qj dot, and sometimes it also depends on the time, so we should include time as well. So this is the functional form of the h. So if you take dh from this functional form, so you will get the del h del qj dqj plus del h del pj dpj plus del h del t dt. Now let's say this is equation 2 and equation 3, okay. Now what you can do, you can equate the coefficient, you can equate the coefficient of dpj in equation 2 and equation 3. Similarly, you can equate the coefficient of dqj from equation 2 and equation 3. And similarly, if you equate this coefficient, what you will get? You will get qj dot. Qj dot should be equal to del h del pj. If you compare equation 3, compare equation 2 and 3, then you will get qj dot. Qj dot is the coefficient of dpj. Qj dot, and here the coefficient of dpj is del h del pj. So that is del h del pj. Similarly, equation 2, coefficient of dqj is pj. Or this will be,
Sir, it is PJ dot.
this is pj dot, right? Okay. This is pj dot. This is pj dot. This will be equal to del h del qj minus del h del qj, and del L del t will be equal to minus del h del t. So these three are called the Hamilton's canonical equation of motion. Okay, these three are called the Hamilton's canonical equation of motion. Okay, these three qj dot. So you guys have to remember. Okay, and if you solve multiple problems, then you will be used to this form of the equation. That qj dot, this is equal to del h del pj, pj dot equal to minus del h del qj, and del L del t equal to minus del h del t. These are called the Hamilton's canonical equation of motion. Okay. Now what I want to do is that I want to show you example so that you guys get to know how to arrive at this problem. If we give you a problem set, how to derive this canonical equation of motion. Okay. So we'll start with this familiar problem of the simple pendulum, and we have done the Lagrangian for this system. Okay, we have already set up the Lagrangian for this system. So now let's set up the Hamiltonian. Okay, so let's say the pendulum bob is here and mass m somewhere, and let's say this length is L, this angle is theta. This is the simple pendulum. Okay, now for this case, we have already derived the expression for the energy. Do you guys remember what was the kinetic energy for this pendulum? Can you guys recall what was the form of the kinetic energy?
L square theta dot square.
Yes, half m L square theta dot square, because this is basically angular velocity. Okay, so and the potential energy you guys already know. This is mgl 1 minus cos theta. Okay, and here theta is the generalized coordinate. So you guys should always remember that this here theta is the generalized coordinate. So the Hamiltonian, Lagrangian was L equal to t minus v. So you can simply write m L square theta dot square minus mgl 1 minus cos theta. Okay. Now here, what is the generalized coordinate? Generalized coordinate. This is theta. So what will be the generalized momentum? How can we calculate the generalized momentum here? Let's say the generalized momentum p theta. Can you guys tell what will be the generalized momentum? How can we calculate the generalized momentum here?
L by del theta dot.
Yes, del L by del theta dot, because Pj is generally del L by del Qj dot. This is the expression. So here you know the Lagrangian. So if you take derivative with respect to theta dot, you will get the generalized momentum. So here that value will be am L square theta dot, right? So this will be am L square theta dot. Now how can we set up the Hamiltonian here? So one way you can set up is H equal to T plus V. Okay. But the problem is that this is not always applicable. This is applicable only when I told you this is applicable only when the system is conservative and L is not an explicit function of time. So if that satisfies the if that condition is satisfied, then you can write simply H equal to T plus V. But in general, we don't set up that way. For in this case of simple pendulum, you can write H equal to T plus V. But this is not always applicable. Okay. So that's why we tried to avoid setting up Hamiltonian using this formula. In general, we set up the Hamiltonian using this formula, this general formula, this Qj dot Pj. Qj dot Pj minus L. In this form, we generally set up. Okay. So here, this is we have only one generalized coordinate, so we don't need to take any summation. And here Qj dot, that is basically theta dot, right? And Pj is basically P theta minus L. And we know the expression for L. We have already set up the Lagrangian. So this is the expression for L. So we can write here this P theta, theta dot minus L. Minus L is basically half m L square theta dot square minus mgl 1 minus cos theta. Okay. So, and P theta, what is the expression for P theta? This is ml square theta dot. Okay. So if we put here ml square theta dot, and here we have half ml square theta dot. So we'll get half ml square theta dot square plus mgl 1 minus cos theta. Now you can see this expression of the Hamiltonian. Can you see the functional form? This depends on theta and theta dot. This is the functional form. But this is not the functional form that we want. We want that H should be in the form of theta and P theta. This is the functional form that we want. We don't want this functional form. So what we need to do, we need to convert all this theta dot into P theta. So whenever you will set up a Hamiltonian, initially you will get the Hamiltonian in the form of theta dot and theta, or in the form of Qj and Qj dot. So from that point, you have to convert the Hamiltonian in terms of the generalized momentum P theta. So here we know the relation between theta and theta dot and P theta from this expression. From this expression, P theta equal to m L square theta dot, we know the relation between this. We know P theta is basically m L square theta dot, or you can say theta dot is basically P theta by m L square. So we will replace theta dot by this expression. Okay, so from here we'll get H is equal to half m L square P theta by m L square plus mgl 1 minus cos theta. Okay. So this is because this is not the form that we want. We do not want theta dot in the expression of Hamiltonian. We want it to be in the form of theta and P theta, generalized coordinate and generalized momentum. Okay. So if we ask you to set up the Hamiltonian, you have to set up in this functional form. In this functional form is not valid. You cannot leave it there. You have to set up in this form, generalized coordinate and momentum. Okay. Now we have the Hamiltonian. So this is the Hamiltonian for this simple pendulum problem. Okay. Now once we know the Hamiltonian, we can set up the Hamilton's equation of motion. And what are the Hamilton's equation of motion? We have just now derived the Hamilton's equation of motions are Qj dot is equal to del H del Pj. So in this case Qj dot is basically theta dot. Theta dot is equal to del H del P theta. This is one of the equation of motion. And what is the value of del H del P theta? Can you see from here, from this equation? Let's say this is equation 1. If you do derivative of this Hamiltonian with respect to P theta, what you will get? You will get this P theta ml square, there will be 1 ml square here. So this will be P theta by ml square. Okay. So this is P theta by ml square. So this is one of the equation of motion. Or let's say this is equation 2. This is equation 2. Okay. And second Hamilton's equation of motion, that was this is, and Pj dot was equal to minus del H by del Qj. So from this expression, what we'll get? P theta dot. P theta dot is equal to, if we do this derivative of Hamiltonian with respect to theta, what we'll get? We'll get this term is 0. If you take derivative with this of the Hamiltonian, the first term is 0. You will have only the second term. And second term is mgl. This will be mgl sine theta. Okay. So this is equation 2 and 3. So these are the two Hamilton's canonical equation of motion for the simple pendulum. This equation 2 and 3 are the equation of motion. These are the this has disappeared. Okay. So here equation 2 and 3 are the Hamilton's equation of motion. Okay. Now we can further simplify. If you know the equation 2 and 3, you can derive the equation of motion for the simple pendulum. Let me connect this one. Are you guys following how we are setting up the Hamilton's equation of motion? This is little bit complicated, I understand, but if you guys have to practice also. Otherwise, if you guys just see now on my notepad, you guys will not be able to remember what you have done. If you do yourself, then only you can remember. Okay. Okay, so
So
equation,
all this derivation can come in exam.
this is not derivation. For the simple pendulum, this is not the derivation. This can come in the exam. We can ask you to set up the Hamiltonian for the simple pendulum and then derive the equation of motion.
Okay, sir.
This is derivation. This first part was derivation, where I derived the Hamilton's equation of motion from this functional form.
Yes, sir, I was talking about this only.
That this is a very simple derivation. This
So
can
this,
come.
okay, sir.
This is 3 or 4 line derivation. Okay, so equation 2 and 3 are the equations of motion. Okay, these are the equations of motion. Now we can simplify equation 2 and 3. We can further simplify. You can see that in equation 2 you have theta dot. Theta dot is equal to P theta by ml square. So from equation 2, let's say from equation 2, if you take another derivative, if you take theta double dot, what will get? Theta double dot will be equal to P theta dot by ml square, right? If you take another derivative of equation 2 on both the side, you will get theta double dot. Okay. Now P theta dot, we have now P theta dot, and you can replace P theta dot from equation 3. Then using equation 3, you will get theta double dot. P theta dot is basically minus mgl sine theta. So here you can say this is equal to mgl sine theta by ml square. So this is equal to G by L minus G by L sine theta. Okay. or you can say this is basically theta double dot plus G by L sine theta is equal to 0. When theta is small, you can say sine theta, this is equal to theta. So from this equation, then you can say theta double dot plus G by L theta, this is equal to 0. And this is the equation of motion for the simple pendulum. And this same form you have derived using Newton's, when you knew the Newton's equation of motion, Newton's laws, and we have also derived the same equation using Lagrange's equation of motion also. So you can see we arrive at the same conclusion, but the formalism, how we arrive at this equation of motion, those are different. Okay. And although this Hamiltonian formalism, it looks much more complicated to you now, but we have several advantages, and I spoke about some advantages in the last class, and we'll discuss at the end again. But what are the advantages of this, using this Hamilton's equation of motion? For the simple problem, of course, this is looking very complicated. Okay. So yeah. Did you guys follow how we are setting up the Hamiltonian? Or if you guys have a question so far, you can tell me if you guys have any problem.
So could you please briefly explain the whole setup again?
For this whole setup, for this simple pendulum.
Yes, sir.
Okay, let me revise again. So where we have started, we have started with kinetic energy and potential energy. Okay. Then we set up the Lagrangian. For the system, and we derive this we find the expression for the generalized momentum p theta. Okay. Now once we know the Lagrangian and the generalized momentum, we can set up the Hamiltonian. Because if you look at the expression for the Hamiltonian, it contains the qj dot and the generalized momentum and Lagrangian. So to set up the Hamiltonian, you need all these three information. You need the expression for the Lagrangian, you need to know the generalized momentum, and also qj dot. These three quantities you know. So that's why first we set up the Lagrangian and determine the generalized momentum. Okay. So then we got the expression for the Hamiltonian. So once we got the expression for the Hamiltonian, so initially it was looking like that this expression depends on, it has the functional form of theta and theta dot. But we want this Hamiltonian to be in the form of theta and p theta. We want Hamiltonian in the expression of generalized coordinate and generalized momentum. So that's why we replaced all this theta dot by p theta. And then we got the final expression for the Hamiltonian. Okay. And once we know the Hamiltonian, then we can use this Hamilton's canonical equation of motion. That these three equations. This you have to remember absolutely always. Okay. That what is the value of qj dot, pj dot, and del L del T. So once we know the Hamiltonian, then using these three equations, we can derive the equation of motion. Okay. And so how did you come to equation 3? Equation 3, I told you del H del qj. So this is basically here p theta. This is basically p theta dot equal to minus del H del theta. So what is the value of del H del theta here? You can see del H del theta is basically mgl. First term is 0. There is no theta term. On the second term, you have mgl 1 minus cos theta. And that becomes mgl sin theta. Is it correct or not? This is minus del H del theta. So this term minus cos theta, this should be minus plus, and cos theta derivative is sin theta minus sin theta. Yes, this is correct. So this is minus mgl sin theta. Okay. And then we have simplified. Once we know the equation of motion 2 and 3, then we have simplified by using this equation 2 and 3, and then we got the final expression. Okay. Let me show you another familiar example. So let me show you another example. Another example using this one, linear harmonic oscillator. Linear harmonic oscillator. Okay. Let us then set up the Hamiltonian and derive the equation of motion. This case also. Okay. So in this case, we know that if you have a block of mass m, which is connected by spring of spring constant k, and let's say this is along x-axis and this distance is x. Okay. Now you guys need to tell me. Okay, I don't want to do myself. You guys need to tell me how should we proceed. So first as I told you, we need to set up the Lagrangian in this case. Okay. So we need to know the kinetic energy and the potential energy, right? So what is the potential kinetic energy in this case? You guys tell me. Okay, then only I'll proceed. What will be the kinetic energy in this case for this linear harmonic oscillator?
Half mx dot square.
Half mx dot square. And what is the kinetic energy? Sorry, potential energy.
Half kx square.
Half kx square. Now what should we do? We have kinetic energy and the potential.
Lagrangian.
So we should set up
Yes.
Lagrangian.
Lagrangian.
T
minus b.
This is equal
So
to.
why there's half mx dot square
So
for
kinetic energy is basically half mv square, right? And v is basically x dot or dx dt.
okay, sir.
Okay, so we have Lagrangian half mx dot square minus half k x square.
X square.
Now what we should do now? We have the Lagrangian now.
We
Hamilton.
have to define Hamiltonian.
We cannot set up Hamiltonian from this. We need another thing before expression for the Hamiltonian is j qj dot pj minus l. Do we have all the information here to set up?
Analyze
No, sir,
momentum.
we have to define qj and pj.
So qj we know. Qj is basically in this case qj is x.
X.
We know qj dot also. But we need to find pj, right? Or px.
Yes.
Del L by del X dot.
So px is basically del L
Del L by del X
del
dot.
x dot, right?
Del
Del X dot is
mx dot.
mx
mx dot.
dot.
mx dot.
So the Hamiltonian, what will be the expression for the Hamiltonian?
X mx dot minus Lagrangian.
So this is qj dot pj minus l. Okay, right? So this we have only one generalized coordinate, so we don't need to take any summation. So
Yes, sir.
this is px and x dot minus l.
Minus L.
Let me write this. This is also half m x
M
dot
x dot
square
square.
minus half
Minus half kx square.
x square. Okay. So I told you. So this is in the here in this expression we have x dot, right? And this x dot we don't want it. This x dot in the Hamilton expression of the Hamiltonian. So how we'll replace this x dot?
Px by m.
Px by n.
We have this expression, right? Px equal to mx dot. So from this expression we can
Yeah.
say x dot is basically
Px by m. Px
m.
by m. M.
So we'll replace all this x dot by px by m, and this will be minus half m px by m square minus half kx square. Okay. So what we'll get? We'll get this is px square by m. This is half m px square by m. This is half kx square. So if you simplify,
Half
you
k square by
get
m.
px square by twice m
And minus half
minus
k square by m.
half
K square by 2m.
So plus आएगा ना, plus half kx square.
half
Plus
there is no
आएगा,
m,
plus
right?
आएगा, हाँ.
Half kx square. So this is the
Plus
Hamiltonian.
आएगा बीच में.
This
So
will be
plus
plus,
half
right?
kx square.
Sir, B plus, हाँ.
Yes, this is plus, right? So this is the form, this is the Hamiltonian for the simple, for this linear harmonic oscillator. Okay. This is the expression,
sir.
final expression for the Hamiltonian.
Yes, sir.
Now we want to find the equation of motion. We want to find the Hamilton's equation of motion. We want to do this equation of motion. So how should we do this? That is Qj dot, that is equal to del H del Pj. Or you can say this Qj dot is basically x dot, right? X dot equal to del H del Px. So what is del H del Px? This will be Px by,
Px by M. Px by M.
so Px by M. So let's say this is equation 2. बाद में होगा 15 minutes बाद आओ, ठीक है? And we have another equation. We have another equation Pj dot. This is equal to minus del H
So let's
del
write
Qj.
that.
And this is basically Px dot. This is equal to minus del H del X. And what is del H del X? This is Kx, right? Minus Kx. So this is equal to minus Kx. So equation 2 and 3 are the Hamilton's canonical equation of motion. Now we can simplify, right? We can simplify equation 2 and 3. So from equation 2, we know x dot is this. So, okay, do you guys know why we are further simplifying? Here we have two equations of motion. Why we can simplify equation 2 and 3 again? Is there any general idea why we can simplify this expression again?
So general coordinate is Qj and Pj dot. That's why we are seeing.
No, that okay, that is Qj and Pj, but that is not the reason we can simplify. Let's say you have two, okay, let me say, you have 2 degrees of freedom, okay? Then how many equations will have here? For one degrees of freedom, we are having 2 equations, right? So now let's say you have 2 degrees of freedom, then how many equations you will have there? Let's say you have r and theta as a generalized coordinate. Then how many Hamilton's equation of motion you will have? So there you will get expression for r dot, p r dot, and again theta dot and p theta dot. So you will get four equations in total, right? You will get 4 equations. But here we can simplify these 2 equations again because you have only one unknown. But if you want to describe this equation, you have only 1 degrees of freedom. So ideally you need only 1 equation, right? You have one unknown variable. So if you need only one equation to describe the equation of motion, right? If the particle is moving in a 2-dimensional plane, you have 2 degrees of freedom. There you will need 2 equations of motion. There you will have 2 unknown and there you will have 2 equations. So here you have basically 1 unknown. If the particle is moving, in this case, in this problem, in this general problem, you have to describe the equation of motion, you need only 1 variable, 1 unknown. Okay. So that's why you can further simplify equation 2 and 3. Okay. So from equation 2, what you will get? You can take derivative again. This will be px dot by m, and px dot is basically minus kx. So you can say this is equal to minus kx by m, x double dot, or you can say x double dot plus k by m x, this is equal to 0. And this is the equation of motion for the simple harmonic oscillator. Okay, and this is the same expression we have derived using Lagrange's equation of motion as well, right? So yes,
x double dot basically means acceleration, right?
yes, x double dot is basically acceleration. This is d2x dt2. x double dot. Whenever we write dot or dot on a variable, that means it's a differentiation. Okay.
Okay, sir.
You guys have this in class 12 or not? This notation x dot.
So we generally used to write acceleration and velocity directly, so not much use of
No,
dot.
not in terms of the acceleration, but this notation you knew or not? This notation.
No, sir.
Yes, sir.
No, sir. No,
A
sir.
little bit.
Okay, sir. Okay, some of you knew and some not. Okay, so whenever we put a dot on a variable, that means it's a derivative of that particular variable. Okay. So if we write x
Sir,
dot,
with respect to
x dot means dx, in general the time derivative. Okay. In general, this is the time derivative because these are shorthand. Okay, we don't want to write this always d2x dt2. This is little, we have to write lot more. So simply you can write x double dot instead of d2x dt2. Okay. If the independent variable, if you look at the expression also, then you will know what is the independent variable with respect to which variable you have taken the differentiation. So in general, in this class, we'll mostly take this will be time derivative. So always x double dot or something dot or double dot will be with respect to time, most of the cases. Okay. Okay, so any doubts so far on this one? How to set up the Lagrange's equation of motion? Sorry, Hamilton's equation of motion. So I'll give you some more problem so that you guys can practice this Hamiltonian. I'll give you both assignment as well as tutorial so that you guys can follow. But I can give you a general recipe how to set up the Hamiltonian. Okay. So the general recipe you can follow this. General recipe for Hamiltonian. For Hamiltonian. So you guys already have done in this case of simple harmonic oscillator. So first what you need to do, first you need to choose the generalized coordinate, right? First you have to choose the generalized coordinate. This is the first task of any problem here. Both in case of Lagrangian as well as in case of Hamiltonian. So first you have to choose the generalized coordinate. So once you know the generalized coordinate, then what you will do? Once you have the generalized coordinate, then what you should do to set up the Hamiltonian? Can you guys tell what you should do after that?
Find kinetic energy and potential energy in the term of general coordinate.
So find T and V, okay, in terms of Qj and Qj dot, right? And then set up the Lagrangian. Lagrangian L in the form of Qj dot and T. So this is okay. So one thing is that in the both the problem we have not considered this term. Okay, del H del T. This is also another equation of motion. Del L del T. Because this equation, these Hamiltonians, they don't explicitly depend on the time. Okay, both this case and in the case of simple pendulum also. But this is the third equation of motion for the Hamiltonians. If you have time explicitly present, then you have to do this also. The del H del T equal to minus del L del T. Okay. So you have to set up the Lagrangian. So once you know the Lagrangian, then what you will do after that? After knowing the Lagrangian,
Generalized momentum.
so then you have to find the generalized momentum. You have to find generalized momentum. This is basically del L del Qj dot. So once you know this generalized momentum, then you can set up Hamiltonian. Hamiltonian will be J Qj dot Pj minus L. Okay. And now in general, this will be depending on both. H will be depend on Qj dot, Pj and T at this point. Okay. In most cases, you will see that these four variable will appear in the expression for the Hamiltonian. But we don't want this Qj dot in the expression in the Hamiltonian. So what you have to do here in the fifth step, that replace Qj dot by Pj. Okay. Qj dot by Pj. Okay. So and then you will get this form H equal to H, Qj, Pj and T. This is the form of the Hamiltonian that we will get after replacing this. And in the sixth step, last step, you have to use this expression that Qj dot, this is equal to del H del Pj, and Pj equal to minus del H del Qj and del H del T equal to minus del L del T. This equation of motion. Okay. So this step you have to follow. If we ask you to set up the Hamiltonian and derive the equation of motion, these are the steps you have to follow. Okay. Any questions so far on this one? If you guys have any question, you can tell me. In tomorrow's class, what I'll do, I'll discuss some of the advantages. I'll specifically discuss some of the advantages of setting up this Lagrangian and Hamiltonian, and then over this Newtonian mechanics, or Newton's laws of motion that you know so far. And then we'll end unit 1. Or do you guys want more example of this Hamiltonian?
Yes, sir. More example.
Okay, then I'll show one more example tomorrow. Okay. But this is the general form. Okay. This is the general form that you can follow to set up the Hamiltonian. Any other doubt regarding the Hamiltonian that you want to discuss tomorrow? Either from Lagrangian or Hamiltonian. You want me to discuss tomorrow? I'll show one example and I'll discuss the advantages, disadvantages. Any other general doubt you have over unit 1 you want me to discuss, or over Lagrangian or Hamiltonian?
Sir,
Yes.
if we have two generalized coordinates, then we will get 4 equations. Then we have to derive 2 equations from those 4 equations.
Yes, from there you should get two equations. If you simplify them, you will get 2 equations. But you will see some of the times these simplifications are not easy. Okay. So depending on the problem, or the question that we will ask, you can leave the answer at that particular point. Okay. If we just ask you to set up the Hamiltonian, then you don't need to derive this equation of motion and then do simplification. But in most cases, you can do this simplification because you don't need 4 equations for a single variable. So from that concept, you should be able to simplify.
Okay, sir.
Any
Sir.
other? Yes.
Reference book.
Reference book, I told you na, this Goldstein book of classical mechanics and Greenwood book of classical mechanics. Goldstein classical mechanics and Greenwood classical mechanics.
Sir, are these books available in the library?
Yes, those are available in library and also online, also easily available. You can check.
And sir, some PYQs also in library are available.
Which one?
So some PYQs, like I don't know how the exam of college looks like. So if
That's why we are giving you the tutorial and the quiz. Okay.
Okay, sir.
Any other question quickly? Okay, if not, then okay, then let me end this class today here, and then we'll meet again tomorrow. Okay. Okay, guys, then bye bye. We'll see you tomorrow.